And I'm going to try to
Recording in progress.
pause every now and after every few questions and start uploading it and switch to another computer so it can be uploaded as soon as possible. So hopefully that will work out. All right, so before we get started, any general questions on anything? If everybody could sign on that paper, just your name and your email address. And I just realized something that I forgot. And so I'm going to be just a couple more minutes. So I'm going to.
Recording in progress.
All right. So the first couple pages of the handout just have formulas that I find useful, things that I use when I'm doing problems on these topics. At the bottom of the third page, I have some formulas that are used that he gives in class for determining the value of a shunt capacitor. That, as far as I know, it's not in the textbook. It's just another way of doing it. What's that?
It's just that, not like the other slopes and stuff, or like just the shunt capacitor. I can just get that like in the problem.
Yeah, we're going to use this in one of the problems. Yeah, I mean the other stuff on here you also need to be able to use, but just this part right here is all you need for that particular problem, and a little background knowledge as well. Okay, so let's start with just some of these sort of concept questions. The relation between resistance, reactance, and impedance. What are those things? This is from the very beginning of the year, but it's related because the angle is related. So what is the relationship between these things? Well, what are these things? All right, I know you know what resistance is. Right, okay. And we know that impedance acts like resistance. So resistance is what you had in circuits 1. That's just your regular stuff. But the reactance is what you get when you convert everything to phasors and you look at the imaginary parts. And the reactance, we have the symbol for that is X. And the symbol for the resistance is R. And the symbol for the impedance is Z. And so we can write that Z, yeah, it might help. We can write that Z equals R plus, they never, as far as I know, they've never cleaned up here like before. And so I don't know why they're doing it now. So the impedance is R plus JX. And it also is true that the Z squared will be R squared plus X squared. And if you drew these in a triangle, if you drew the resistance in this direction and you drew the reactance in this direction, and
I have a question.
Yes.
Are we supposed to be seeing something?
You absolutely are. Thank you for asking. Thank you. And please don't hesitate to speak up because I will forget. I'll forget to share the screen and I'll forget to record. Did someone knock or is that just my imagination? Okay. So if we look at this angle between the resistance and the reactance, and we look at this angle here, this angle phi, that's the same as the angle that we get when we're talking about power. So that's the same angle there. Because if you multiplied each of these things by I squared, so if I multiplied this by I squared and this by I squared and this by I squared, then what I would get from that is the Ri squared. That's our real power. And Xi squared, that's our reactive power, that's Q. And Zi squared, that is our apparent power, that's S. And so that's the relationship between those things as well. And the units of each, our units for power are going to be watts or kilowatts. Our units for reactive power are VAR, volt amperes reactive, and our units for apparent power are volt amps. And a volt amp is equivalent to a watt. They are equal to each other. It's just we have these different terms so that we can kind of keep track as to which one we're talking about. Okay, so let's say we had a purely resistive circuit. So what do I mean by a purely resistive circuit? Just think about the words.
Resistors,
Yeah, and no what?
no imaginary.
Yeah.
ones.
Yeah, so no reactance. So if I had a purely resistive circuit, what would be the phase difference between the voltage and the current? When you were in circuits 1 and you had just resistors, did you ever talk about, and you were just doing DC, did you ever talk about a phase difference between voltage and current? So in a purely resistive circuit, the phase difference is 0 degrees for purely resistive. Purely resistive. And what do you think it would be if we had a purely reactive circuit? Or just look at our picture up here. Well, it would be 90 degrees. You can't tell unless you say leading or lagging whether or not you're talking about, like which direction your 90 degrees is, if it is ahead or behind. And I already answered 4. So these things, and you can also see them on our first page. When we look at right here, so I have I squared X is Q and I squared R is P. It's real power or real average power, and I squared Z is the apparent power. So we have those. Also, I am frequently asked, when do you use this 1/2 and when do you not? You don't use the 1/2 when you have the root mean square, and you do use the 1/2 when you have peak. So if they give you the peak or they don't tell you it's root mean square, then you do use the 1/2. Okay, so let's talk about this power factor. And I know it's not presented this way in class, but I find it really helpful to think of the real power and the reactive power and the apparent power as a right triangle, because in fact they are. And you'll see this when you take power. And so this is the power triangle. This is the real power, so that's P. And P is VI cosine phi. And you have the reactive power, which is Q, which is VI sine phi. And you have the apparent power, which is just VI. And it is also true that S squared equals P squared plus Q squared, because it's just a right triangle. And this phi right here is where we get our power factor from. And so when we talk about the cosine of phi, that's our power factor. And if you look at the triangle here, then it's easy to see that the cosine of phi, where that comes from, is that's P over S. So that's your real power over your apparent power. And then if you draw this triangle, all the rest of the formulas make sense as well, because they all come from this triangle. So given that, when would the power factor be 1 and when would it be 0? So if the cosine of phi is the power factor, and if that equals 1, when do we have cosine equal to 1?
At 0.
Thank you. And so if it's 0, if our angle is 0, what does that tell us about the kind of circuit that we have if this angle is 0? So this would be that we have a purely resistive circuit. So power factor equal to 1 means we have all real power. All the power is real, so all real power. And if our power factor is 0, that means that it's all reactive power. I'm going to pause for a minute and just ask, is this seeming very clear or not? Just trying to get a feel. Makes sense? Is it helpful? Okay. All right. So this was just to kind of give you some basic understanding of the different kinds of power, because I know when I took Circuits 2, when I was studying for this test, I just had all these formulas and I was just using them and I didn't really know what I was doing, and I didn't really understand it until after I took power. So I thought I would try to explain that a little bit. Okay, so the next few examples are going to be short examples, again, just to kind of get used to things before we jump into some of the harder stuff. So we have a wound coil that has an inductance, in other words, we have an inductor, of 180 millihenries, and we have a resistance of 35 ohms that is connected to a 100 volt, 50 hertz power voltage supply. Calculate the impedance of the coil, the current, the power factor, and the apparent power consumed. Okay, so what is our impedance going to be? So we'll have J omega L for the inductor plus 35 for the resistor. So we'll have 35 plus J times, now what's omega? Two pi times 50. So it's the frequency in hertz times 2 pi. So 2 pi times 50 times L, which was 180 millihenries, so 0.180. And so I believe, and somebody please check me on this, that this gets us 35 plus J 56.6. See if I installed my calculator. I'll get it in a minute. come back to that later. Okay, did y'all get same value? 56.6? Yes, okay. All right. So that's our impedance. Okay, so now we need to get the current. So how do we get the current?
This is the voltage over the.
Sure. So the voltage is the current times the impedance. So I'll take the voltage over the impedance, and that would get the current. So that would be 100 angle 0 over 35 plus J 56.6. And I got when I did this 0.79 plus J negative 58, no, negative 1.27. Negative 1.27, which became 1.5 angle negative 58 degrees. Does it make sense that the angle would be negative? So let's talk about Eli the Iceman. Okay, so what does Eli the Iceman tell us?
Current lags voltage.
Current lags voltage in what kind of circuit? Yeah, in the inductive circuit. Okay, so not everybody knows what Eli the Iceman means. So would anybody like to explain how we knew that? Where did we come up with that? I had no idea what Eli the Iceman meant for years. I heard it said all the time. I had no idea what it meant. Wow. Nobody wants to talk? Okay, so E is a symbol for voltage, just like V is. And so E is voltage and I is current. And so when I have ELI, L is the inductor, so I can see that the current lags the voltage because the I comes after the E in Eli. And then if I have the capacitor, I have that the current leads the voltage. And so in our particular current circuit right here, it's inductance, and so we would expect that the current should lag the voltage. And so our current has an angle of negative 58, and our voltage had an angle of 0. So that does make sense. So we agree that that's correct. Okay, and then the apparent power consumed. So the apparent power consumed, we can do this in different kinds of ways. I think the easiest way, since we have everything here, is to say that the power equals V. I like using this one. The power is V times I conjugate, since we have everything right here. And so the V is just 100, and I conjugate would be 1.5 angle positive 58 degrees. And so this would be 150 angle positive 58 degrees, and this would be VA. And so our angle here is 58 degrees, and so our power factor is cosine of 58, which is 0.53. And yeah. Okay, any questions on any of that before we move on?
Power factor have a unit?
It does not have a unit. It's a good question.
In this case, I know it's not asking, but is it leading or like you said it's lagging? I'm gonna ask like those questions I'm gonna ask to state that.
Oh, right. So you'd have to state whether it's leading or lagging. And so in this case, so which would it be here? It would be lagging. And so it's lagging because a couple ways we can say that it's lagging. First of all, we know it's lagging because it's an inductor. We also know it's lagging because our current and our angle of our current is less than the angle of our voltage. But the main way that I would know is because it's an inductor. But then also if you do the math and we get this number here, that tells us as well. Okay, so other questions? All right. So a power factor correction. So the reason we care about all this is what you can use is the real power. And so the reactive power may make it seem like you have more power than you do. And so a power factor correction helps you bring the power factor from a lower number to a higher number to get it so that more of your apparent power is real power. And you can do that by adding a shunt capacitor, and by adding the capacitor you can make your power factor closer to 1. So that's what a power factor correction is. So now I have let's see. Let's pause for a minute, and I'm going to save this recording and upload it, and we'll come back and we'll work these problems. So I'm going to stop this and upload it.